Good afternoon, ladies and gentlemen. Welcome to this IMechE webinar event. Thank you for joining us today. My name is Andrew Fraser. I'm the chairman of the IMechE Automobile Division. It's my pleasure to be acting as your host and chairman for the event today. Just before I introduce the speakers, two very good speakers today, just a reminder to please make use of the question function. You'll see the question box in the upper right-hand side of the screen if you wish to table questions. That would be helpful. We should have approximately 20 minutes for questions at the end of the event. We do have quite a large audience today. We're expecting quite a large audience, so I'll apologise in advance if we don't get to all the questions. I'll do my best to try and group them if I can, or pick some of the key ones of interest, but apologies up front if not all questions do get addressed. But please use that facility to make for a lively question session at the end. Also, just to mention that the overall event is being recorded, and there will be recordings available on demand after the event to everyone who has registered for the event. So if you're unable to scribble notes fast enough, don't worry, there will be an opportunity to review the content later on. Thank you for that. So yeah, my pleasure to introduce our two speakers for today, Dr. Marco Cecotti and Dr. Efstathios Velenis, both from Cranfield University Advanced Vehicle Engineering Facility, two very notable figures in this field. Marco's an electrical engineer by background, and then did his doctorate in the field of controls and controls activity. Efstathios, similarly, but sort of complementary, degree in mechanical engineering, and did his PhD in aerospace engineering. So two very well qualified experts in the topic of autonomous vehicles. So looking forward very much to hear their presentation. They're going to do it together, so it's nice having two presenters join together on this topic, very much on the field of connectivity. So I think that's probably enough from myself, and I'll pass you over to Efstathios and Marco. Thank you very much, and I hope you enjoy the event.
Thank you very much, Andrew. So I'm Dr. Marco Cecotti, and I will start this presentation. Then I will give the control to my colleague Efstathios. So today we're going to talk about future developments in the area of autonomous ground vehicles. And we're going to start by giving an overview of the current state of the technology, and by covering some of the projects that we worked on that are looking at how to develop this technology forward. And then we're going to dive more specifically into the Human Drive project, the Muka project, and then I'm going to hand over to Efstathios to cover the 8CAP project and the Cranfield's approach to bridge the skill gap that the automotive industry is facing in this area. So what about the current state of autonomous vehicles? You might be aware that very recently, in 2021, a few companies have just started to offer fully autonomous vehicles for the transportation of people to the general public. The most famous ones are Waymo and Motional, and they are all based in the US. We also start to encounter autonomous vehicles on other day-to-day activities, most notably the delivery of groceries. And I put a picture on the bottom right of one of the Starship vehicles that have started to appear in several cities in the UK. So obviously, we don't know exactly all of the technical details of the implementations of different manufacturers, but we know roughly the state of this technology and how they usually work. And they all tend to follow a reference path unless there is an obstacle in the way. They are often remotely connected to a control center to supervise their operation, but also to allow remote driving when unexpected obstacles are encountered. They cannot be dealt with the standard autonomous system. However, they are not designed to communicate with other road user or the infrastructure. Also, they tend to interface with the base vehicle exactly in the same way like human drivers do, by setting targets for tractive torque, braking torque, and steering angle. And we at Cranfield, we believe that all of this this way of operating autonomous vehicle can be improved upon. And we are going to present you 3 projects that address exactly these points. We'll start with the Human Drive project, which look at the way humans position their vehicle on the road, adapting to the presence of different road actors. For example, it's fairly common for a human driver to see a pedestrian walking very closely to the edge of the road and giving them space, or giving space to an oncoming car on a very narrow road. Then we're going to talk about the Muka project, which focused on connected and autonomous vehicle, and looked at the ways these vehicles can share information with each other to improve performance and to cooperate together to coordinate their movement during emergency situation. And finally, we're going to look at the ACAP project, which look at the way multiple actuators, typically controlling the torque and the steering at each wheel, can be used to achieve safer and faster maneuvers. So let's start with the Human Drive project. This was a very large project that lasted for roughly 3 years and ended in March 2020. It was managed by a consortium of several companies, universities, and public bodies. And the overall budget of the project was around £14 million. The consortium was led by Nissan, and Nissan European Technical Center in particular, and they led the development of the autonomous vehicle. I forgot to mention, that the overall aim of the project was to develop an autonomous vehicle with human-like performance. Hitachi, in particular, was in charge of developing the machine learning-based controller to mimic human-like trajectory planning and perception. University of Leeds took advantage of their advanced driver simulator and actually run experiment with hundreds of participants to understand how human drivers behave and to build a human driver model. Connected Places Catapult was responsible for project management, communication, and marketing activity, and to build the safety case for the project. Highways England was looking at the requirements for the road infrastructure for autonomous vehicle deployment. And us, Cranfield, we were responsible for the validation of the vehicle on the proving ground, particularly the proving ground that we have on Cranfield campus. IMechE was looking at the impact of autonomous vehicle on the transport system, and Myra provided test facilities and supported the safety case for the project. Atkins was responsible for the cybersecurity framework, and SBD led different studies on cybersecurity for autonomous vehicle and human-machine interface. So, why is human-like behavior needed? Generally, it is required in situation where a reference path is not obvious or it is likely affected by the behavior of other road users. And these situations are common in urban scenarios, But this project didn't focus particularly on these scenarios, and instead focused more on the situation that arise in country roads, particularly country roads that are narrow, they don't have road markings, they have high-speed passing cars, potholes in the way, and that modifies the trajectories of vehicles. No curbs, so often we find all sorts of road users in the middle of the road, and so on. One of the objectives of the project was also to demonstrate autonomous driving on a long journey across the UK. And we called this the Grand Drive. The journey that was chosen for this project went from the Nissan European Technical Centre, which is based in Cranfield, to the Nissan plant in Sunderland, covering roughly 230 miles across a variety of terrains, including country roads, complex roundabout, motorways, merge, and multi-lane changes. The Grand Drive was completed at the beginning of 2020, so in the middle of winter, and therefore the vehicle had to deal with limited visibility due to reduced sunlight hours and to all sorts of weather conditions, as you can see in the picture, typical grey winter day in England. And obviously that to deal with the many roadworks that characterize the M1 and the motorway system in general. And of course, it was successful. You can find a video online and more information online. The vehicle drove autonomously for almost all of the journey, apart probably something like a couple of minutes along the whole journey when the driver had to take over in some particularly challenging situation due to roadworks generally. I'm going to show you a quick video that summarizes the output of the project. I'm going to enable the audio. So this is the proving ground in Cranfield campus. You can see the airport on the left. So just to clarify, this video was put up together before the Grand Drive was completed. But yes, eventually it was successfully demonstrated. Let's go back to the other microphone. And I thought you might be interested in the hardware that was used on this vehicle. The system relied on 8 laser scanners, 6 of which were mounted on the front and rear bumper of the car. fairly low on the ground, and 2 of them were 360-degree spinning LiDAR mounted on the roof rack. The system relied on 7 cameras, 4 mounted on each side of the vehicle, like in a standard surround view system, and 3 of them mounted behind the windscreen. And a radar at the front was used to confirm the detection of object at the front. The system relied on several computational units, 6 PCs for the perception and the control system, and 2 vehicle control ECU for ensuring that the trajectory were accurately followed. I show in this picture just a representation of what the vehicle could see. So on the left, you see the output of the free space detector detecting the road ahead of the vehicle. And on the right, you can see the object recognition algorithm identify vehicles straight ahead in front of the vehicle with a red box, and oncoming vehicles that are approaching the vehicle trajectory with the green box. Just going to show you how the vehicle operates around roundabout. So this is a video taken during fully autonomous operation. And if you keep an eye on the top right box, you see that cars are very fast approaching, going around the roundabout without necessarily indicating what they are doing. The vehicle is stopping and checking that the roundabout is clear and moving ahead. Just a few words on how we validate the behavior of the vehicle on the proving ground. We effectively replicated over and over different scenarios using road actors driving cars, and this is just an example of a single lap. We had a routine of 6 laps in which we were testing the behavior of human drivers. So we had about 20 participants driving these 6 laps, both as passengers of the autonomous vehicle and as human driver. And then we compared the positioning of cars of the vehicle, of the autonomous vehicle, and the human drivers. And you can see that some of the interactions include emerging of a vehicle from a T-junction, or overtaking a vehicle that is stationary in the middle of the road. We also had some interactions with pedestrian crossing in front of the vehicle or moving along the vehicle. Now I'll move on to the Muka project, whose focus is to develop a cooperative approach for connected and autonomous vehicle to handle dangerous situations, particularly to avoid collision. The Muka project was managed by a consortium made by 6 partners and led by IDIADA. IDIADA was responsible for the vehicle and electronics integration, the development of a custom vehicle control unit, and the development of software and testing of the overall systems. Cranfield was responsible to develop algorithm for sensor fusion, collision avoidance, and to develop a human driver model, and to model the vehicle dynamics of the chosen autonomous system. Cosworth was in charge of the perception system, Connected Places Catapult for the systems engineering, Westfield for the testing oversight, and Secure by Design was working on cybersecurity. So with this slide, I would like to explain you roughly how the system that we developed works. So obviously, we want to deploy the system on standard on the future autonomous vehicles, and we cannot establish a hierarchy across vehicle on the road. So it should be a distributed system where every car counts equally and is not coordinated by a supervisory controller. So we were inspired by the way human drivers negotiate difficult situations, and they use the turning indicator to communicate a desired maneuver, but they also have a backup plan in mind in case the traffic around them cannot move out of the way. And so we developed this system in which there are two trajectory planners in each vehicle, and one of them calculates a planned trajectory, assuming that all of the vehicles around us, they maintain their trajectory. And at the same time, another controller calculates a desired trajectory if the vehicles around were allowed to move. So the planned trajectory is calculated considering the planned and the desired trajectories of other vehicles, and the desired trajectory is calculated only considering the desired trajectories of other vehicles. And these allow us to cascade forward the desire of multiple cars to move in a given direction. I'll give you a simple example, looking at the use case on the top right, where we have two cars driving on a multi-lane road like a motorway, and initially the lanes are free. So both cars have a desired trajectory and a planned trajectory that goes straight ahead. Then M2 start approaching an obstacle, and therefore the planned trajectory start to plan a braking maneuver in front of the obstacles because there is a car on the left of M2, and it's not possible to move in their way. At the same time, it broadcasts the desired trajectory to move on the left. M1 receives both of these trajectories and checks whether it can accommodate the desired trajectory of M2. And in this case, it's a simple case. There's no one on the lane on the left of M1, so it can directly plan a new trajectory that gives space to M2, and then it communicates this to M2, and M2 can enact this its originally desired trajectory, which becomes the new planned trajectory. If there was another car on the left of M1, M1 would not change the planned trajectory, but express the desire to move on the left, and the other car would decide whether it can accommodate this or not, and then cascade the planned trajectory to M1, and then to M2, and so on. So a model predictive controller was used to maximize the distance from the other vehicles. So it was effectively the trajectory planner, and kept comfort into consideration as well. Because we want to deploy the system in a mixed traffic scenario with standard cars on the road, we also develop a human driver model to estimate the trajectories of vehicles that cannot communicate a desired and a planned trajectory. I'm just going to give you a brief overview of the system architecture. It was focused on a single controller developed by IDIADA, very small, could fit in the well of the spare wheel, was based on an NVIDIA Jetson, containing a safety micro, differential GNSS positioning, and an inertial measurement unit, cellular modem, a Wi-Fi system, and V2X radio. I'm just gonna close with the video of the final demonstration. I hope you like it. Sorry, I forgot to change the audio. back.
Vehicles approaching some dummy obstacles. For the sake of this trial, what we do is set up the situation using safety drivers, then they both hand over control to the computers. Muka has control. And then the computers are entirely responsible for cooperatively steering the cars round the obstacles, working together, using their vehicle-to-vehicle radio links until the scenario is complete. This is the first time that anyone has demonstrated full-size cars working cooperatively together. It's like a hive mind or a shoal of fish. Avoiding collision. Here we just have two connected research vehicles, but in future, all vehicles on the road can be connected. And the implication of that is that they can work together for cooperative collision avoidance like this. About 1,500 people a year die on the UK roads, and our objective is to reduce that number through automated collision avoidance of a really advanced kind. The Muka Project, it's funded by the UK government, by the Centre for Connected and Automated Vehicles, with a total budget of £4.5 million. We've been running for 2.5 years now. So these tests are the very culmination of the project. The partners to the project.
Okay, I'm just going to stop because I know that we are running out of time. So I'm going to hand over. I'm going to hand over to my colleague Stathis for the presentation of the IMechE project. Just change this. You go.
Thank you. Thank you, Marco, and good afternoon from myself. And thank you everyone for attending our presentation. I will carry on with a presentation of another one of our recent projects in the area of autonomous vehicles. This is a project that was funded by Innovate UK through the CAV3 funding competition. The name of the project is IMechE, which stands for Advanced Integrated Dynamics for Connected and Autonomous Vehicles. The project was led by Delta Motorsport, one of our collaborators that we've worked with in previous projects as well. And the project brought together 4 UK SMEs and 2 research organizations with the aim of delivering novel technologies in the area of actuation of autonomous vehicles, namely the development of drive-by-wire, steer-by-wire, brake-by-wire technologies. At Cranfield, we were responsible for the development of control algorithms to deliver path-following control, the lower level of the autonomous vehicle control hierarchy, which takes advantage of the available actuation. And in this particular case, we're talking about independent steering of the front and rear axles, as well as independent torque control, which is commonly known as torque vectoring. And in addition, we are looking at developing controllers which are capable of controlling the autonomous vehicle in extreme operating conditions, including the limit of handling. Just a few words about the motivation behind our work. The introduction of several actuations within the chassis of the vehicle, such as differential braking, torque vectoring, active differentials, front and rear steering, and so on, has mainly been done in the context of human-driven vehicles and has enabled the development of active safety systems and advanced driver assist systems with very important impact in the safety of passenger vehicles. At the bottom right side, you can see a depiction of the classical electronic stability control, which uses independent braking of each of the 4 wheels in order to eliminate excessive understeer and oversteer of the vehicle during emergency cornering. So the introduction of this several actuators has been used for many, many years. And a lot of those systems, most of those systems, they share a common feature, which is effectively that they aim at delivering stable, intuitive, predictable behavior of the vehicle for the average human driver. And this is typically achieved by limiting the operation of the tire within low slip conditions, as depicted on the top graph, the green highlighted area within the typical tire force versus slip characteristic. We are aware, however, that there are very capable human drivers, expert human drivers. Normally we see them at racing environment, who take advantage of the behavior and the performance of the vehicle outside the envelope enforced by such systems. So an expert driver may apply a handbrake input in order to lock the rear axle and to perform a very tight turning radius at high speeds in a rally environment. So indeed, expert human drivers may operate outside that envelope in the red highlighted area of the tire characteristic. So the question that we are asking here is when we are removing the human driver from a highly automated vehicle, a driverless vehicle, is it still sensible to develop systems that limit the behavior of the vehicle, that effectively deliver an intuitive response of the vehicle for the average human driver? Or should we be looking at creating controllers with expert knowledge of vehicle dynamics and expert skills in controlling them? So not necessarily to drive in a racing environment, but effectively to drive the vehicle safely in adverse conditions where the limits of handling are quite low. So in this project, we're looking at exploiting the available multi-actuation, the available control authority of modern vehicles in order to control autonomous vehicles in extreme limit handling operating conditions. So as I mentioned, our work focused on the lower level of the control hierarchy of the autonomous vehicles, which is the path following control. So we assume that perception has taken place, that motion planning has taken place, and the task of the controller is to actually follow a prescribed predicted path as long as different states as necessary. For instance, the controller may want to, we may wish for the controller to deliver tracking of a path at a particular reference speed. And in our work, we also extended that task to following further states of the vehicle, such as the side slip angle. The context here is to exploit the available actuation. So we're looking at control design, a multivariable control design. We need to have a control synthesis which is able to operate with a vehicle at the limit of handling. So in the presence of important nonlinearities and constraints. And hence, we decided to develop our controller in the context of model predictive control. This is an optimal control formulation, which is solved in a receding horizon, nonlinear constraint optimization fashion. So why we decided on this approach is because we are able to incorporate the nonlinearities of the vehicle dynamics, and we are able to incorporate multiple control inputs for the multi-actuation requirement, and also to accommodate important constraints. This is an overview of the development framework, starting from model derivation. In this particular case, this is an extremely important step because we are looking at a real-time optimization solution. So the model needs to be able, from one side, to deliver accurate information about the limit behavior of the vehicle, and from the other side, it needs to be efficient and of low enough order in order to allow real-time calculations and optimization. These models were developed in simulation environment of MATLAB and Simulink, We incorporated the state-of-the-art optimization algorithm provided by Embotech. The program was called Forces Pro. Before we moved to real testing, we did a lot of validation in high-fidelity simulations, such as CarMaker. We validated the real-time applicability of the controller using hardware-in-the-loop testing. And finally, we performed extensive testing at our own facility, part of the movie testing grounds at Cranfield, which allows for vehicle dynamics testing. I think the next one is a short video, which I will probably play. Sorry, let me change the audio settings first. And go back to here. So maybe just for the sake of time, I can start from a little bit further ahead. First, you will see some of the visualization of the simulation results. We were able to create effectively a digital twin of the facility and to design our testing maneuvers in this simulation environment. And you will see the same maneuver being executed by the vehicle in our on the right hand side. You can see some of the important information: the vehicle, the velocity, the side clip angle, which we were all as well, and also the acceleration diagram, the diagram. So the approach to the this last handling test, the typical constant health basis test, we were able to deliver best function, and in order to demonstrate the advanced capabilities in control of the limit handling of the vehicle of our controller. So let me swap back to audio. And so this was a short overview of the IMechE project. And may I move quickly then to addressing the skill gap. I can introduce some information about our teaching activities at Cranfield University. Perhaps you are aware that Cranfield University is unique in being a solely postgraduate university in the UK. And within our group, the Advanced Vehicle Engineering Center, which is divided in 4 core sectors: automotive, motorsport, intelligent mobility, and off-road dynamics. We offer 5 specialized MSc programs, namely automotive engineering, which is the first of its kind in the country, and it's run now for nearly 60 years. More recently, we introduced the automotive mechatronics program, for which I'm the course director. We have the advanced motorsport engineering program, which also runs for, I believe, around 30 years, and more recently, the advanced motorsport mechatronics program. Only last year, we introduced the connected and autonomous vehicle engineering MSc, which specifically focus in this particular area. So between the automotive mechatronics and the connected and autonomous vehicle engineering MSc, we address some of the key areas of training and skills that engineers need to develop in order to address the area of technology development in autonomous and connected vehicles. The automotive mechatronics program effectively has a 40% of its credit value is assigned to the taught part, which includes a core automotive engineering topics such as vehicle dynamics, powertrain, vehicle electrification and hybridization, and so on. And then there is a mechatronics specialization set of modules in modeling, control, embedded systems, and specific vehicle applications. On the right-hand side, you can see some of our facilities in tire testing, four-post rig, hardware-in-the-loop facilities, and so on. One of the things that we are that we put a lot of focus on in our programs is the project work, the group project and the thesis project, which we put a lot of emphasis, such as most of the projects that we offer are in collaboration with our industrial contacts, who are able to deliver additional supervision, access to facilities, access to data according to the particular need. Being conscious of the time, I think I will just move on to the next slide, and I will invite back Marco, who is one of the course directors.
Hello again. So yeah, as Tati said, I'm the Deputy Course Director for the MSc in Connected and Autonomous Vehicle Engineering. Most of the qualities that Statis mentioned apply across our courses, actually. And I'm going to add a few more qualities that also apply across our courses. So we do our best to provide hands-on experience with vehicle prototypes on our proving ground, and to engage with relevant businesses through the usage of an industrial advisory board that we form for both our automotive courses and our motorsport courses. And effectively, we invite members of industry to attend the event at the end of our group design project, where we present the outcome of the project, and another event at the end of the individual research projects, where each student present a poster generally of their work. And we also have a short session with the board to gather feedback about the areas that we are teaching and whether we should align them better with their needs. We also try to involve our industrial partners in group projects and individual research projects, both just by proposing a topic and by engaging with the supervision if they are interested in it. Specifically to the MSc in Connected and Autonomous Vehicle, we try to offer a broad taught program, followed by the opportunity to specialize or to try different things through the project, the group project, and the individual research program. Very briefly, this is the structure of the course. We have 10 taught modules of 10 credits each that, as I said, covered roughly all of the topics that are related to connected and autonomous vehicles, and then a relatively short group design project compared to the other courses, and 4 months of individual research project at the end. And just to give you an idea of what our students covered, we've done work on perception, on airside obstacle detection of moving clusters in 3D point cloud. We worked on decision making, like overtaking policies for racing cars on an oval track. We've done trajectory planning at the limit of handling, and we've done some conceptual design for autonomous tug systems for aircraft, or on-road evaluation of the state of health of the road. And that brings our presentation to the end. So please.
Excellent. Thank you very much. That was really interesting. I'm definitely not an expert in autonomous or connected vehicles myself, so I found that very fascinating. I spent my career at Ford in a more conventional vehicle environment, so that was really interesting. Thank you very much, gentlemen. That was an excellent coverage. Are you okay if I pose you some questions now?
Yeah, absolutely.
We have quite a few. They're all fairly specific to the topic, I think, so I'll try and get through as many as I can. First one is from John Hambley. He asks, autonomous vehicles need a significant amount of real-time, high-performance computing. The electrical power requirement is significant. Will battery capacity in future electric vehicles be a barrier to the adoption of autonomy?
I think the power requirements to power the powertrain greatly dominate the power consumptions for batteries. So yeah, I think it would be not very significant, the power required by the autonomous system, comparable to the power used by the air conditioning.
Do you have a figure for actual power or a target that the system would consume in watt hours per
varies
kilometer?
Greatly, but I would be surprised if it exceed 1 kilowatt. So yeah, I'm not aware of any autonomous vehicle that takes more than 1 kilowatt for the autonomous system.
Okay, so yeah, so 1 kilowatt hour per hour would be quite modest compared with the propulsion power. Okay, yeah. Very good. Thank you. No, that's good question. Right, question from Alan Broomhead. On the Grand Drive, how often did the human driver have to intervene, and under what circumstances?
Good question. Unfortunately, I don't have the exact answer. I believe they had to intervene to park the car during breaks. They were forced to take breaks, so the human supervisors were forced to take breaks because it's a 4.5 hour journey, and they had to park the car manually in the service station. And I think that was the main interruptions. And I don't think so. The Nissan ran 3 Grand Drive, so maybe there were some specific instances in one of them, but yeah, the general situation where this was necessary was parking in the service station.
Thank you. That's brilliant. I guess I find that quite interesting, as there are quite a number of autonomous parking systems on the market now in conventional vehicles, which allow the vehicle to park itself under a limited
yeah, but I identify a parking space in a completely unstructured environment like a car park of a service station is pretty challenging. So I think the parking maneuver by itself, it's okay, but navigating the service station is slightly more challenging for a system that is designed to drive on the road.
Okay, that's good. Great, thank you. Next one then, if we may, from Michael Buxton, one of your colleagues at Cranfield, it looks like. He asks, is there a threshold for objects that the system will break or swear for? Is it coded or just in the image resolution? Presumably, he says, presumably it will react to a human-sized object, but not to insects. So what about rabbits, pheasants, cats? So I guess the question is, what's the smallest object that the system will try to avoid? Interesting one for the cat lovers out there.
Yeah, it's an interesting question. There's no standard, so it strongly depends on the vehicle and what the manufacturer decide to do. I don't know what was the case for the Nissan vehicle of the Human Drive project. Quite normally, there is a threshold of size that is built into the perception system, so very small objects are not detected or are ignored. They are also not detected by the radar, typically. So the perception system applies some filtering, and then I think we could have a decision-making process in between that identifies stones on the road and detects that we can drive over them. But I don't think this is very common. Generally, these exceptions are handled by the safety driver. Quite commonly, the perception system detects anything that is unexpected on the road as well. So it has a pre-recorded map of the road. And if there's something that doesn't look right, then it flags it as a problem and stop the car before reaching it, regardless of the size.
I hadn't particularly thought about it, but it is a very interesting topic. Yes, what size? And I guess the human driver has a perception of the likely effect of hitting the object. If it looks solid, they may choose to try and avoid it. If it looks soft, they may, like a cardboard box or something, they may choose to run over it. It's quite an interesting question, actually. Yeah, interesting case. Good. Anyway, it's not up to me. So here's a question from William Campbell. He asks, how can you test corner cases with machine learning algorithms when artificial intelligence has an opaque logic? How big is it a challenge to satisfy the likes of ISO 26262?
Wow, that's a challenging question. I mean, it's a hot topic in the validation of autonomous systems. So unfortunately, I don't have an answer straight away. But quite commonly, you can treat a system as a black box and track the boundaries at which the system fails. So as soon as you identify a failure case, you can then modify the parameters and understand when the system doesn't fail anymore, and track these boundaries to understand what are the parameters of the scenarios that make the system fail. And then I guess you need an expert to evaluate whether these scenarios are likely enough to cause an issue for your system, or they always would cause an issue, but sometimes they are so unlikely that we can rely on the system anyway. So,
very good, thank you.
I hope this answers the question.
Thank you. I will leave it up to the questioner to decide, but sounds very relevant. Thank you. Question on the Muka project, quite a specific one. What is the effective maximum proximity of the vehicle-to-vehicle communication systems? So I guess how far apart can they be before they can interact?
I think the one we used covers something like 150 meters. And there is also the option to relay the messages to other vehicles, so to create a mesh network effectively. But yes, the focus of the system is to exchange information with vehicles very nearby.
Good, thank you. Another interesting one on testing systems from Ben Wentworth at the MOD, actually. He asks, how important is the accumulation of driving data and the capture of edge cases in the development of autonomous vehicles? Is it likely that whoever leads the race in the capture of edge cases will win the race to develop a level 5 autonomous system? Good question.
Probably. Certainly, companies like Tesla are competing to gather as many information about the performance of their, especially machine learning algorithm, as possible. Now, I think there is a significant effect of simulation that needs to be considered, and I think simulation will address most of the validation cases that can be experienced. But yes, there are also some weird situations that test engineers cannot even foresee. And so it's important to detect this with real life testing. I believe there are some regulations that are already in place and some are coming into place that will oblige the automotive company to publish a detailed report at the very least of near misses and accident. And so hopefully this will reduce the gap of the available information between large companies and the competitors.
Oh, interesting. So there's a proposal to actually force the sharing of those edge cases. Oh, that's
yeah, absolutely. I think it's already in place in the US and it's under discussion as well.
Okay. Perhaps a complementary question then. A question from Joel Barath. Are there projects to develop infrastructures to complement or aid autonomous vehicles? I guess our infrastructure was designed around 150 probably years of human drivers. Are you aware of any developments to change that to suit autonomous vehicles?
There are research projects in the area, but yeah, I'm not aware of any large-scale projects to deploy infrastructure for autonomous vehicles. I believe we are still strengthening the communication protocols, the information that would be required So currently there's a little bit of uncertainty about what the autonomous system needs, and therefore there's no public body that is willing to invest for some infrastructure to provide this information. But there are lots of efforts and to build standards in this direction, and group of large automotive companies are working together to define what is required. So hopefully it will happen in the future, but not over the next couple of years, I think.
Thank you. In the more general field, then, there was a report recently of a truck managing to drive across America autonomously. The questioner Ian Borthwick asks if you have any observations or any comments on that piece of development.
I'm not aware of that project, unfortunately. So I don't think I can add anything. I don't know. Status.
I remember seeing it, but only high level. I didn't remember the technical content, but yeah, an large semi-trailer truck was reported to have driven, and they commented, because the autonomous system could drive continuously, how much faster it was able to cross the continent than human drivers who had to take breaks. I remember that detail in it. I can't remember the numbers, but it was quoted as being a lot more efficient in terms of product delivery, because there were no need for the drivers to stop and take breaks.
Yeah, I think motorway driving is probably where we'll see the faster development of autonomous system, because it's a fairly well-structured environment where there's not a lot that can happen. I mean, a lot of things can happen, but they are very unlikely. And it's fairly easy to detect obstacles ahead, because the road is fairly smooth and uniform. So we'll probably see several features, either advanced driving assistant feature with partial autonomy on the motorway.
Thank you. I guess maybe I could ask a question just linked to that, because in the introduction of the video, they talked about the safety aspect, but most accidents occur away from motorways, usually in urban environments. So deploying autonomous systems on motorways will perhaps have much less of an impact on safety than the perhaps more difficult urban environments. Is that a fair comment?
Yeah, absolutely. I think the biggest impact, well, it would allow long journeys on the motorway. I think that's the big advantage, reducing the effort the drivers need to put into driving through these long journeys. But it would not affect particularly the safety of the overall road network.
Thank you. I appreciate that. Okay, back to questions from our audience then. There's a lot flowing in, actually. Sorry, I won't get to all of them in the last couple of minutes. We may have touched on this already, but a question from Tom Leggett at Thatcham. He asks about, to what extent do you see virtual testing replacing physical testing when assessing autonomous vehicles?
I think it will be the dominant way of testing autonomous systems. It's just very hard to cover a large mileage with a prototype. So I think that's the only way to test extensively the system, and hopefully when a certain level of robustness is achieved, probably they will try and deploy it like Tesla is doing with their autopilot, which is not an autonomous system, but it goes in that direction. And I assume the company will try to gather information from what's happening on the road to their customers. There will still be testing on the road. I don't think this will disappear ever, and on proving ground as well. But it won't be able to cover all of the scenarios that can be covered in simulation.
Thank you. Right, we're virtually at the end of time now, so I'll go with the last question here now from David Coleman, ex of JLR, actually. It says, in the narrow country lane scenario, human drivers might drive into the vegetation in order to make enough space to pass an oncoming vehicle. Is this a sort of pragmatic rule that that AVs are capable of doing like humans do? So,
I think that's what we expect from autonomous vehicles. We are not there yet. I think they are not often. They are not able to recognize different types of vegetation and whether the vehicle can get damaged or not. But that's the ultimate aim. I think we should expect that, because otherwise they will not be able to drive in the narrow lanes that we can find in our country roads.
thank you. No, that's a good question. I like the question, and thanks for your answer. Yes, because as someone who lives in the country and is familiar with that, yes, you make immediate judgment on, oh, there's some grass or some bushes there or some nettles that I can swing through, but if there's a tree, you don't really want to swing a foot off the road to allow the tractor that you meet on the bend coming around the corner, which, yes, does happen quite regularly. No, thank you very much. Gentlemen and audience, apologies. We are at the end of our allotted time, so I've tried to get through as many of the questions as possible. Apologies, didn't quite get to all of them, but I hope we've covered a good flavour of the topic. So it only really remains to thank Marco and Efstathios very much for an excellent presentation, really interesting. Some great to see the range of work going on, physical road testing, virtual work, track testing, huge range, and some excellent skills there. Some of those diagrams of control systems I do vaguely remember from my university course, but I have to admit being a little bit rusty, but nice to see examples of some of the skills and capabilities that we need in students and engineers in the future, particularly in that sort of software and control systems environment, and probably some read across between automotive and perhaps aerospace in some of those areas, I would imagine quite strongly. So thank you, Marco and Efstathios. That was excellent. Much appreciated giving the time and the overview, and I hope the audience found it interesting. And I'll close there. Thanks again.
Thank you very much to the audience for the interesting question, and thank you, Andrew, for chairing the session.
Pleasure. Nice to meet you.
Yes.